This is problem 23 from chapter 14. The 8-kilogram block is moving with an initial speed of 5 meters per second. If the coefficient of kinetic friction between the block and the plane is 0.25, determine the compression in the spring when the block momentarily stops. So I said here to find S. That's the S that we have in our equation here for the force of this spring. But remember that S is equal to L minus L naught, where L naught is the undeformed length of the spring and L is the deformed length of the spring. And so when the spring is compressed, S is negative. And this is when the block momentarily stops, so the velocity at that point is equal to 0. We're going to use our work-energy relationship here, and the first thing that we get to do is cross a lot of things out in this equation. So the block is not touching the spring to begin with, so the length of the spring initially is the undeformed length, so the elastic potential energy is equal to 0. So this is 0. And then we could also say, since V2 is equal to 0, the final kinetic energy is equal to 0, and the height of the block is not changing. And so mgh1 is equal to mgh2, so this and this cancel. Before we rewrite our equation, let's also look at the other forces that we would have to consider for the work that we have here. So I have the normal force acting upward, I have the force of gravity acting downward, but the normal force doesn't do any work because it's perpendicular to the displacement. The displacement is horizontal and to the right. I have a force of gravity acting downward. I already accounted for that with my gravitational potential energy. When the block is against the spring, we have the force of the spring acting on the block, but I already accounted for that with the elastic potential energy. So I only have one force left, and that is the force of friction. It's kinetic friction in this case. And whenever you do the dot product for the work with kinetic friction, it's always going to be negative because friction always opposes the motion. So if the displacement is to the right, the friction must be to the left, and therefore the dot product here is going to be negative. So now let us rewrite the equation. So we have 1/2 times the mass times v1 squared, and then I'm going to put the negative sign in, and so this is the magnitude of the force of kinetic friction. Ooh, and the magnitude of dr, which is ds, which I don't know that I like that in this case because it's different than this s, but I called this s2, so maybe I'm okay with that. So this is 1/2 k s2 squared. Okay, so I'm trying to be consistent with the notation that they use in the book, but I find the notation that they use in the book to be a little confusing. So if you want to call this dr instead, maybe that would be better. Okay, so we have 1/2 times the mass, which is 8 kilograms, times the initial speed, which is 5 squared, minus the force of kinetic friction. So to find that, I'm going to have to look in the vertical direction. And do you remember in a previous problem when we were looking at the box, which was sliding on the half cylinder, we had to look in the normal direction? So we're going to have to do the same thing here, although here it's the direction which is perpendicular to the displacement. Yeah, it would be the normal direction, except in this case we don't know if the normal direction is pointing up or pointing down. But in any case, we have to look in the direction perpendicular to the displacement in order to find the normal force. Since the block is not moving in the vertical direction, we have the normal force is equal to m times g. Therefore, the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So that's just 0.25 times the mass, which is 8 times 9.81. And that gives us 19.62 newtons. What am I going to do with this? Well, it's a constant force, so I can pull it outside. So this is 19.62, and then I just have the integral of ds. So that would be the distance from here to where the block is when it stops moving temporarily. In order to try and make this s the same as the s that I have here, I'm going to say that this is when s is equal to 0. And so then the block is starting at -2 and going to, I'll call it S2 because this is S2. And then, oh, I know what K is, so let's call this 200, and this is S2 squared. Okay, so I have 1/2 times 8, which is 4, and 5 squared, which is 25, and 25 times 4 is 100. So this is 100 minus 19.62. Then when I integrate ds, I get s. I put in the limits of integration, and I get s2 minus 2. Actually, that's supposed to be minus -2, so that would be plus 2. And at this point, I realized that I made a slight mistake when I defined s to be 0 here and said that this would be -2. Because back at the beginning of the problem, I said if I'm looking for s and the spring is compressed, s is supposed to be negative. Although when you look at the elastic potential energy, it's not going to matter whether S2 is positive or negative because you're squaring it. And the way I define things here, that was assuming that S is positive, which is a lot easier to work with. So maybe I just want to say the absolute value of S2, and then it agrees with what I have here. And I don't have to worry about the fact that it's really negative. And this is equal to 100 times S2 squared. And so then I have 100 minus 19.62 times S, the absolute value of S2, plus 2 times 19.62, which is negative 39.24, and that's equal to 100 times S2 squared. And then 100 minus 39.24 is minus 60.76, and then I want to bring this over to the other side of the equation. Well, actually, we could just leave it like this. And you can solve for S2 using the quadratic formula or your calculator, but if you're using the quadratic formula, you might prefer to rewrite this one last time. We bring this over to the other side, it's positive. And this over on the other side is positive also. This is equal to 0. And that didn't work out so well because I messed up the sign here. This is plus, so this is minus, and then we get two solutions. One is positive and one is negative, and in this case I want to choose the positive one because I have the absolute value of S2 in here. So that will be absolute value of S2 is equal to 0.688 meters. And actually, I think I'll just leave the answer like this because they asked me to find the compression in the spring, they didn't really ask me to find S. I just said I was going to find S. So the spring compresses 0.688 meters. So that's the answer to problem 23. My suggestion for you when you're doing problems like this is maybe just use a different letter instead of S so you don't have two different S's, and that will hopefully make things much easier. And then if you're using the elastic potential energy, it doesn't really matter whether S is positive or negative because you're squaring it. And then if you just call this something other than S, there should be a relationship between the final position and the compression of the spring, but I think I would just avoid trying to use the notation that they use in the book because it just made things rather complicated. Okay, so that concludes problem 23.